just bear with me. I'm more in the medical view now, so just go slowly with what we can. I'm just going to go real slowly. Anatomy, I think most of you are climbers and know about the pulleys, but just to remember what they are made of, we have two angular pulleys which are attached to bone, which are the A2 and A4 pulleys. We see them most often ruptured in pulley ruptures. There's one that's not attached to the bone, that's the A3 pulley, that's attached to the roller plate, and less important, the C1, C2 cruciform pulleys are not, well, we don't consider them as important. What happens when the pulleys are removed, the tendon moves away from the bone and you can't really properly flex the finger anymore. When we look at a pulley in a cadaver or when we operate on pulleys, you can clearly see them. They're like shiny, much stronger than the tendon shaft. And I was amazed when I saw my first pulley on a cadaver. It's really, really strong. If you've ever heard a pulley rupture, I think you know why it is that strong. It's quite a strong structure. When a pulley ruptures, there are several ways to manage a pulley rupture. However, if there's a multiple pulley rupture, as you can see on the right, we recommend a repair, and this is what I'm going to talk about. There are several repair methods, and they've been investigated in studies. I'm just going to go on to talk about two. The most important one, and that's been shown to be the strongest pulley repair, is the Bonnell pulley repair with 1 1/2 loop. You take another tendon, most often, well, I'm going to talk about how it's done. And the one that has been proven to be the most functional is the Wiley Kleiner repair. Just to show you how it works, in the 1 1/2 loop, you take another tendon that you don't use, most often it's the palmaris longus tendon, you remove it, and then you lace it around the proximal phalanx 1 1/2 times, passing underneath the extensors, because then if you pass it over, I don't think I know. So yeah, so you pass it underneath and then you stitch it back onto itself after 1 1/2 loop. And then the Wiley repair, another repair technique, you use again the palmaris longus tendon if it's there, and you lace it like a shoelace through the remaining stumps of the pulley that has been ruptured on the tendon shaft. And you go back and forth, and that way you have a longer distance that you can cover with the repair. And that's probably why it's been proven to be more functional. The problem with 1 1/2 loop that we've seen is that the extensor tendons tend to be kind of irritated because there's like a structure underneath, and when you move the finger, the extensor tendons go over them all the time, and that kind of irritates the extensor tendons. We've had several patients complaining of that irritation, even leads to a block where they can't really move their fingers anymore, it just stays stretched or in a flexed position. We also were able to notice an intermittent inflammation that led to actual bone loss of the cortical structure in the proximal phalanx, probably as a consequence of reduced blood flow, and that kind of worried us. And we've had several climbers complain to us that the structure is pretty big, and they couldn't wear their rings anymore, as it's the ring fingers most often, you know, so they had kind of problems with their wives at home. So the relative thickness is a problem. This is two patients that we were able to show where you can see the actual bone loss in the radiographs as a consequence of the reduced blood flow of that tendon graft. So the idea was to actually drill a hole in the proximal phalanx, do the 1 1/2 loop across that hole that we drilled, and then proceed using the Kleiner repair that was strong, that led to good functionality. We combine the two and not, you know, lead to bone loss or whatever. However, we're not so sure that if we were going to do that, whether the proximal phalanx would actually hold, you know, because like drilling a hole through such a small bone leads to weakening of that bone, and we were kind of afraid that if we did that on patients that they would just, you know, break their fingers as a consequence of it. So we decided to try cadavers first. And we used the force transducer that we've been using in several studies before. We used cadaver fingers. We inserted them into that machine. Andreas Schweitzer actually invented it. He's going to present a talk tomorrow. And we were able with this machine to pull on the fingertip and at the same time record the forces in the flexor tendons. We used a 1:2 force ratio, which was wrong. And then we were able to record the forces at the bone when something would break. This is how we prepared our specimens. We would first remove all the pulley and the tendon shaft, and then drill a hole, pull the flexor, pull the palmaris longus tendon through, repair it onto itself, and then proceed with the wildly repair all the way up to the A3 pulley. And then we would insert it into the machine and pull until something happened. I'm not going to show you any videos of that. It's not so pretty. And we compared it to fingers that we did not operate on. We removed everything but left the tendon shaft and the pulleys intact, and then we looked at what happened. So with the intact pulley system, 7 fingers had a pulley rupture, which was pretty much what we expected. In one finger the tendon ruptured, and in one finger the screw broke out of the bone, and the finger just, with the pulley repair, we had a failure of the tendon graft at the distal end. So the tendon graft actually did tear, but only at the distal end. Our 1 and the 1/2 loop always remained intact. 2 fingers broke out of the screw, and 1 finger dislocated in the PIP joint, and the most important thing was that we really had no fracture at the drill hole, so the bone never broke. When we recorded, the forces recorded at the moment of something happening were much higher in the unrepaired fingers, which was to be expected because they had all their pulleys intact, whereas the one that we had worked upon had no pulleys intact. However, the differences were not so extreme. I would have expected more difference. So the most important thing for us was really that there was no fracture of the bone at the side of the drill hole, and that the 1 and 1/2 loop never broke. That was kind of surprising. Only while we repaired for it. The forces recorded were high in the intact pulley system, but that's probably due to having more pulleys, and that there was no possibility of this whole thing actually, growing into. There was no growth, tissue was dead. We're talking about cadavers, so there was no growing in. Forces were about comparable, so we were kind of, that was what we wanted to see, right? No breakage of the bone, and our 1 and 1/2 loop remained intact. So we decided to go on with this, and we tried it on several patients. I actually repaired multiple pulley ruptures using this new repair, and this is a video intraoperatively on one of the patients, just to give you an idea how well this works. And you can see that it actually slides, right? There's no resistance. It's quite smooth. That was our main goal, that we wouldn't impair the flexor tendons either. And then this is after healing. And there's no cortical atrophy. It actually grew into the bone. We had good results. The patients are still pretty well with this, climb to the full level. We've really achieved what we wanted to achieve, and the transosteal modification gave them everything that they wanted, and they can still wear their wedding rings and